Today's lecture on EKGs will cover EKG leads. This lecture will be relatively packed with important information. The learning objectives will include, first, to understand the basic concept of an EKG lead. Next, to know the 12 conventional EKG leads and the angles from which each lead views the heart's electrical activity. To know the proper location of the 10 conventional EKG electrodes. And finally, to be able to correlate specific groups of leads with anatomic regions of the heart. Let me start by explaining what an EKG lead is. A lead is a view of the voltage between 2 points, known as poles, as a function of time. The positive pole for each lead is marked by a single recording electrode on the body. The negative pole for each lead is marked by either a single recording electrode or a virtual electrode known as a central terminal, which averages input from multiple other electrodes. Although they are frequently used interchangeably, a lead is not the same as an electrode. An electrode is the physical conductive sticker attached to either the chest wall or a limb through which electrical potential is measured. Different leads, that is, different combinations of positive and negative poles, allows the clinician to view the heart's electrical activity from different directions. In the event that your personal background in circuits is a little shy of an electrical engineering student, some of this may already be sounding difficult to grasp. Don't worry, I'm going to slow down just a little bit, and we will be revisiting this description throughout this lecture. If you stick with it, I guarantee it will make more sense by the end. Since this lecture is covering proper placement of electrodes, I wanted to show what the setup looks like for recording an EKG for those of you who haven't actually seen it yet. First, we need a patient. I hope this cartoon figure will suffice. Next, we need an EKG machine. There are many different shapes and sizes of devices that record EKGs. The ones used in most American hospitals are typically the shape and size of an unusually large laptop computer, often attached to a small rolling cart, as opposed to the coffee table pictured here. Now the patient needs some electrodes. As mentioned earlier, a conventional 12-lead EKG uses 10 electrodes. These usually look like rectangular black stickers, one on each limb, and 6 across the anterior and left lateral chest wall. Each electrode is connected by a separate wire to a junction shown here, which then connects to the machine. The electrical recording then shows up on the screen, and if satisfied with the quality of the data recorded, the clinician can print a hard copy, usually on red or pink grid paper. Here is what a 12-lead EKG looks like. This is exactly what prints off the machine. In the separate lecture on EKG waveforms, I reviewed what electrophysiological event each of the individual little squiggles represents. Now let's talk about why the waveforms look different as one moves across the page. That's because as one moves across the page, the leads that are displayed changes, typically every 2.5 seconds. For example, first are these 3 leads, which are known as the standard limb leads, or occasionally the bipolar limb leads. They are designated by the Roman numerals for 1, 2, and 3. After 2.5 seconds of that recording, next across are the augmented or unipolar limb leads, AVR, AVL, and AVF. I'll discuss what those letters stand for in a few moments. Then there are the 6 precordial leads, labeled V1 through V6. Finally, on the bottom half of the EKG are the rhythm strips. Unlike the top half of the EKG, in which each lead is recorded for 2.5 seconds, the bottom half shows 10 continuous seconds of 3 specific leads. This specifically helps with the identification of unusual rhythms, particularly those that are irregular. Typically, leads V1, 2, and V5 are the 3 leads shown in the rhythm strips. Those are not random choices, as V1 and lead 2 are the leads in which the atrial activity is usually the most prominently seen. I don't know this for a fact, but I would guess that V5 is included as it comes close to having an orthogonal direction to the other 2, as we'll soon see. I won't talk any more about the rhythm strips today, but they will come up from time to time in future EKG lectures. I'll now discuss the three major types of leads, starting with the standard limb leads. For reference, here is a torso with a rib cage drawn in, and I'll make it just slightly transparent to reveal the approximate location and orientation of the heart inside. The standard limb leads date all the way back to 1903, when Wilhelm Einthoven invented the first practical EKG. He attached recording electrodes to the right arm, left arm, and left leg in order to create the three standard limb leads. First, lead 1 has the right arm as the negative pole and left arm as the positive pole. Next, lead 2 has the right arm as the negative pole and the left leg as the positive pole. Finally, lead 3 has the left arm as the negative pole and the left leg as the positive pole. The electrode on the right leg isn't used as part of a lead, but is rather used to ground the system. If your knowledge of electric circuits is limited, just remember that the right leg is not included in the leads, but the EKG will not record unless the electrode is attached. These three leads make a nice little equilateral triangle, but I can imagine that some of you are scratching your heads because the left leg is obviously not located at the umbilicus as shown, and therefore these leads as shown are a substantially inaccurate ideal realization of what the geometry actually is. This is something that bothered me quite a bit when first learning EKGs, seeing lots of diagrams very similar to this one. All I can suggest is not to worry about it and just accept that this triangle is actually a much better description than it seems it should be. In fact, this triangle is so important that it is given a specific name, Einthoven's triangle. And Einthoven's triangle demonstrates an important relationship called Einthoven's law. It is usually stated simply as lead 1 plus lead 3 equals lead 2. What this means more specifically is that at any given time, the voltage as measured by lead 1 plus the voltage as measured by lead 2 must equal the voltage as measured by lead 3. I'm going to set the standard limb leads aside for a moment and move on to the augmented limb leads. One of the early challenges Einthoven faced was that his three leads only provided a very limited view of the heart's electrical activity. It could only observe that activity from three directions. In order to increase the number of directions from which the heart can be viewed, the EKG machine also uses a central terminal. As mentioned before, the central terminal is made by connecting the right arm, and left leg electrodes together. This results in a virtual negative terminal that is composed of the average of the electrical potentials from the three limbs. The creation of the central terminal allows the recording of three new limb leads, one for each of the right arm, and left leg, with the F of AVF standing for foot. By definition, the leads AVR and AVL are 30 degrees away from the horizontal. We'll see in a minute how that angle can be defined so precisely. With the augmented leads, as you might guess, the A in front stands for augmented. This refers to the fact that the voltage recorded by these leads is too small to be compared alongside the other leads, so they must be amplified. This was originally done by manual rearrangement of resistors, but is now done automatically with a microprocessor. The V that sits in the middle of the three-letter acronym used for each augmented lead apparently stands for voltage and is present in any lead that uses the central terminal as the negative pole, including the precordial leads. As with Einthoven's triangle, this collection of leads has an interesting and important relationship. AVR plus AVL plus AVF equals 0. That is, at any given point in time, the voltages as measured by the three augmented limb leads must cancel each other out. We can now combine the augmented limb leads and the standard limb leads into a unified reference system known as the hexaxial system. Imagine a two-dimensional plane using polar coordinates such that 0 degrees is defined as pointing to our right but the patient's left, and positive 90 degrees is pointed straight down. Now superimpose the directions of those 6 limb leads. This is the hexaxial system. Let me give a simple demonstration as to how the hexaxial system allows us to understand the patterns of electrical signals in the heart. During ventricular depolarization, the first major event is a left to right depolarization of the interventricular septum. As viewed from the front of the patient, the wave of depolarization from this event is angled down and to the right. The next major event is the near simultaneous depolarization of the bulk of the right and left ventricles. The next depolarization vector for this event will be the sum of the depolarization vectors for each ventricle. As the left ventricle is normally much more massive, the sum is weighted in a decidedly leftward direction. What do these two electrical events look like as viewed from each of the 6 limb leads? First, in AVL, the initial event of septal depolarization is in a direction nearly opposite that of the AVL lead. Therefore, there will be an initial negative deflection on the EKG recording of that lead. Despite that the two directions are nearly anti-parallel, that is directly opposite, the amplitude of the negative deflection is still only moderate because the amplitude of the depolarizing wavefront in the heart is relatively small. The second depolarization event is of a sort of similar direction as AVL, so therefore AVL will record a later positive deflection, the amplitude of which is similarly influenced by both the angle and magnitude of the depolarization vector. I'll now walk my way around the EKG leads. Because the first depolarization vector is not in as complete an opposite direction from lead 1 as it was relative to AVL, the initial negative deflection in lead 1 is not quite as deep as AVL. However, the second depolarization vector is in nearly the same direction as 1, so therefore the later positive deflection as recorded by this lead is taller than it was into AVL. When it comes to lead 2, the lead is nearly perpendicular to the first depolarization vector, therefore there is negligible initial deflection. The second depolarization vector makes a similar angle to 2 as it did with AVL. Therefore, the later positive deflection in lead 2 is similar in amplitude as that in AVL. In AVF, both the first and second depolarization vectors are in a sort of similar direction as the lead. Therefore, both deflections are positive, but are relatively low amplitude. In lead 3, the first depolarization vector is in nearly the same direction as the lead, so the initial deflection on EKG is positive and large relative to the initial deflection in other leads. The negative depolarization vector is sort of angled away, so the later deflection on EKG is negative. Finally, in the AVR, the first depolarization is perpendicular to the direction of the lead, so there is negligible initial deflection. The second depolarization vector is in a nearly completely opposite direction, so that second deflection on the EKG is negative and very prominent. One way to check your understanding of how these leads look at the heart's electrical activity is to pause the video at this point and double check the mathematical relationships between the leads. That is, at any given point in time, the amplitude of lead 1 plus that in lead 3 should equal that in lead 2. Also, at any time, the amplitudes in AVR, AVL, and AVF should cancel one another. Interestingly, modern EKG machines only directly measure leads 1 and 2, and the other 4 are calculated using these equations. You should not bother committing these equations to memory. I have only listed them here to help you understand how we can know the exact angles at which these leads intersect. They aren't based on the individual anatomy of the patient as much as precisely defined mathematical relationships. So far, all of the leads I have been focusing on, that is, the 6 limb leads, all lie in the same plane known as the frontal plane. It is the imaginary plane that divides the body into front and back halves. If these were the only leads available to us, we would only have an understanding of the heart's electrical activity in 2 dimensions. In order to observe and understand it in 3 dimensions, another set of leads within a different plane are used. These are the precordial leads. There are 6 precordial leads which examine the heart's electrical activity in the transverse plane, sometimes known as the axial plane. The positive pole for each precordial lead is at a location on the anterior or left lateral chest wall, while the negative pole for each is the central terminal. The leads are named V1 through V6 as moving right to left. The specific location to place the electrodes for the precordial leads is very important. Electrode V1 should be placed in the 4th intercostal space, just to the right of the sternum. Electrode V2 should be placed in the 4th intercostal space, just to the left of the sternum. V4 goes in the 5th intercostal space in the mid-clavicular line. V6 in the 5th intercostal space in the mid-axillary line. V3 goes halfway between V2 and V4. And finally, V5 goes halfway between V4 and V6. I feel compelled to stress that the placement of these 6 electrodes by various healthcare professionals is usually incorrect. The most common mistake is to place V1 and V2 in the 2nd or 3rd intercostal space instead of the 4th. Another frequent mistake is for V5 and V6 to not be lateral enough. While these errors won't lead to erroneous conclusions about the rhythm, and are unlikely to lead to erroneous conclusions about bundle branch blocks and ventricular hypertrophy, small misplacements of precordial electrodes can dramatically change the appearance of T waves. The consequence of this, particularly when comparing a correctly recorded EKG to an incorrectly recorded one on the same patient but at a different time, will be an erroneous conclusion about the presence or absence of myocardial ischemia. This can lead to the inappropriate triage of someone with chest pain or possible anginal equivalent. So that is our set of 12 EKG leads, 6 limb leads in the frontal plane, and 6 precordial leads in the transverse plane. How do these two sets of 6 relate to one another? We'll need to understand that in order to understand the true representation of cardiac electrical conduction in 3-dimensional space. Here's the frontal plane with its leads, and here's the transverse plane with its. Now here they are overlaid on one another. I wish I was good enough with 3D modeling software to make this rotate around, but hopefully this view provides you an idea of the spatial relationship between leads. Understanding the spatial relationship isn't just an academic exercise. It also is necessary to appreciate the anatomic correlation between groups of leads and specific parts of the heart. The best EKG leads to probe a specific chamber or wall of the heart are usually those lying most directly over top of it. Because of this, leads are often grouped anatomically. For example, leads 2, 3, and AVF are known as the inferior leads, as they most directly evaluate the inferior wall of the heart. V1 and V2 are known as the septal leads, as they lie over that structure. V1 and V2 also lie over the right ventricle and are the primary leads to examine when right ventricular pathology is suspected. V3 and V4 are the anterior leads, as they lie over the anterior wall of the left ventricle. The tricky group are the lateral leads. Hopefully with a 3-dimensional representation here, you can appreciate that leads 1, AVL, V5, and V6 are all in a similar direction and are the best leads to evaluate pathology of the lateral wall of the left ventricle, and more generally, the left ventricle as a whole. Finally, as you can see, AVR is sort of the odd one out, with no other leads in a similar direction, and thus it has no group assignment. I'm going to end this lecture by returning to a full 12-lead EKG to review the anatomic correlations in this format. Once again, leads 2, 3, and AVF are the inferior leads. V1 and V2 are the septal leads. V3 and V4 are the anterior leads. 1, AVL, V5, and V6 are the lateral leads. And finally, AVR is ungrouped. With some experience, these anatomic groupings will become second nature. That concludes this lecture on EKG leads. Please remember to like or share the video if you found it helpful, or post a comment if you have any questions. At this point, I recommend continuing on to the lecture on rate and axis.